Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at logical quantifiers. We looked at connectives in a previous video, but now we're going to add two symbols. Now, unlike connectives, they don't connect statement. The point of these quantifiers is basically to tell us how many or which things a statement applies to. So let's illustrate what these two mean with these two statements here. So this first statement says, for all x in the set z, x squared equals 4. So this z here is how we write shorthand for the set of integers. This basically means is a member of. So this is saying every integer satisfies the equation x squared equals 4. So that is obviously false. Not every integer, when you square it, gives an answer of 4. On the other hand, this statement here says there exists an integer such that x squared equals 4. There exists an integer that you can square to get to 4. And that's, of course, true. There are, in fact, two integers you can square to get 4. Of course, 2 and negative 2. So this quantifier means there only has to be one case that satisfies the statement. This one says that every single case must satisfy the statement. So we can use these quantifiers in very simple proofs in logical deduction. So the logical deduction we're looking at is called modus ponens. So that is, if you have a premise that A implies B, then if A is true, you can conclude that B is true. So let's look at this statement here. Any soccer player is smart. So rewriting this statement here using quantifiers, I can write it like this. This says for all S in S, PS applies. So here I'm letting this big S be the set of all soccer players, and PS is just the property of being smart. What I'm saying here is that any member of the set of soccer players, so any soccer player, has this property, and this property is being smart. So another way of thinking about that is that if S is in S, so that's basically saying if someone is a member of the soccer player set, if someone plays soccer, that implies that they are smart. They have the smartness property. So this is like our A being a soccer player, and this is like our B being smart. So we're told any soccer player is smart and James is a soccer player. So we're being told that A is true. So A implies B. A is true means that B is true. It means that James is smart. So these two statements are called a premise. They're like what sets up the argument. They're like the information that you have, and then we can use our rule here to make the conclusion that James is smart. So that follows from the previous two arguments. You don't want to make a non sequitur argument where the conclusion does not flow from the premise. But if A implies B and A is true, then B is true. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.